We're starting another topic, yet again. You'll see there's a certain rhythm to the class. Every week or 2 weeks we do something new. But all in the support of this larger narrative about how do we come to understand the world. So we started with dynamical systems, saw how rich they were in terms of chaotic behavior, spontaneously generating complicated behavior due to their nonlinearity. They change radically between these different complicated behaviors as you vary control parameters. That was the topic of bifurcation theory. Then we focused more in on how they evolve probability distributions, and that set us up to talk about measurements. And then that led us into symbolic dynamics. The product of this multi-week argument is now we are going to focus on discrete valued stochastic processes, focusing on the particular question of how can we extract from particular sequences, or maybe I'll give you the word distribution over sequences, how much can we extract about what's hidden in the box? And there's just a long list of questions and things we've been maybe using some informal language to describe. Unpredictable chaos. We had eventually a quantitative notion of how to measure chaos. That was this geometric notion of the Lyapunov exponents. Last problem on the midterm, Lyapunov exponents, classifying high-dimensional behaviors. And that's one picture. The Lyapunov exponents, the way we've talked about them, require you knowing the equations of motion. So it kind of begs the question. I mean, it's fine if you're an analyst and trying to understand things like you're doing. Well, just want to see simple nonlinear systems. How complicated are they? Give us some handle on their complicated orbit sets. And we have these number of dimensions of instability, positive Lyapunov exponents, and the magnitude of the exponents was how unstable things were. And I argued very quickly that they related to the loss of initial information we had about the system. The Lyapunov exponent was some sort of decay rate. If I specify the state of my system to 1 part in 1,000, and every second the system loses 1 bit of resolution, has the Lyapunov exponent of 1 unit, 1 factor of 2 amplification. In 10 seconds, you don't know where the system is. So we're actually going to come back to that, but now with enriched vocabulary using some of the ideas from information theory. So the rest of the quarter is going to be talking about information theory and what kinds of measures we have from information theory. First of all, just to think about what is information and how does that relate, first of all, to measuring the unpredictability of these stochastic processes. So, titled the lecture, Entropies. That's a little bit of a historical crossover between what was essentially an engineering discipline, communication theory in the mid-1940s, and thermodynamics. And we'll come back and talk a little bit about the sort of physics versus engineering view of what information and this entropy quantity is. So now we're shifting over back to textbook reading and exercises and whatnot in the Cover and Thomas elements of information theory. Just the first couple chapters to get us started. And today I'm just going to try to motivate the notion that Claude Shannon introduced in the 40s for measuring information. The citation to his original papers are in the supplemental reading list, and at some point, I feel like most people should read those papers. They're 2 published back to back. Together, they were published as a book about 80 pages long, but it's sort of readable. It's always good to go back to the original sources sometimes. Sometimes they really know how to write. But just chock full of ideas that led to several revolutions in technology and science. In fact, we're still, in some sense, Shannon's been revived in the last half dozen years. So definitely worth reading his original. And they're available in his reprints, Dover reprints and things like that. So easy to get access to. And worth reading at some point. After we get through the elementary things, it's nice to go back and see how concisely Shannon could lay out the main ideas in just a few pages. So what is information? Well, we have, I guess, colloquially been talking in the context of dynamical systems, stochastic processes, that there's some sort of randomness out there. And for now, I'll kind of call that apparent randomness. And what I mean by using the word apparent is to get us to think consistently about an observer looking at a system. You might, someone trained in the physical science would think, well, I usually don't worry about the observer if I'm building, a bridge or running an experiment. Although, of course, quantum mechanics suggests that we have to do that. But I was pointed out a lecture or two ago, actually, because classical dynamical systems are chaotic, we also have to worry about observers. So apparent here is we're going to be thinking about us down at the end of the chain, and this data is coming in, and we have all these sort of observations and tentative conclusions about what's going on in the data. So there were at least two kinds of uncertainty or randomness we've talked about so far. One was, if you think back to the dot spreading experiment, sort of uncontrolled initial conditions. There was some small little square in this state space of the system inside of which I couldn't exactly determine the initial conditions, and that had a consequence. Right? That interacted with the diverging flow so that that initial and microscopic, very small level uncertainty became macroscopic. We couldn't tell where the attractor was, the attractor state, where the system state was on this big chaotic attractor in just a very short period of time. And so the most obvious new notion of randomness was that these deterministic chaotic systems actively produce surprise like that. So okay, we can't control systems exactly, so there's some degree of uncertainty. Can't prepare them exactly, and also there are mechanisms in simple but nonlinear physical, biological, and chemical systems that actively make complicated solutions. So other sources of randomness are sort of regularities we're ignorant of. Now I'm talking just a little more generally. We really don't have a vocabulary set of techniques to talk about this, but it sort of makes sense. If I don't really know when I'm looking at some turbulent fluid, the balance of forces, then my ability to describe that or interpret the measurements or use that to make predictive theories is hampered to the extent I don't know what these are. But that also begs the question. Somehow over the decades, humans, through this scientific view of the world, presumably have come to understand new things, which were different forces and different phenomena in the world. So, an overriding question in this, beyond just doing prediction and measuring uncertainty, is how do we come to learn new things about the world out there? That there are new forces, new phenomena, and how do we develop theories? Presumably at various periods of time, generally new ideas have been injected into the scientific development. Then there's also kind of a flip side of this. Things can appear to be unpredictable or unknown, uncertain to us if we had, say, a limited capacity to build models, a limited cognitive capacity. So if I fall asleep at night, I'm drooling on my pillow, but there's my book from the Argentine writer Borges opened up to his really nice essay, Library of the Infinite, and a housefly comes over and sees this, as it flies over the book, it sees this sort of light and dark sort of undulation. I assume it's not reading Borges, right? Whereas just before I fell asleep, I was reading it and understanding these things. So obviously the world is structured, at least there was some structure for me when I was reading the book, but when the fly flies over the type on the page, that's just luminosity variations to it and maybe not so terribly relevant. Well, maybe I speculate here. It doesn't have the cognitive capacity to understand Borges. Right, okay, an extreme example of how the limited capacity can, to build a model of the world can make the world look. In this case, you'd think, oh, it just makes the world look more random. But the houseflies and us, we cohabit, right? Perfectly legitimate existence on Earth, and they've co-evolved with us. They obviously are picking up something in the world relevant to them. So it's perfectly functional, the subset of sensory stimulus, and they have a way of using what that is. But they presumably have a very different way of representing what's going on. Still effective, but different way. So there's an interaction between, or if you had a machine that had very, very limited memory, then you wouldn't expect it to build descriptions of very complicated systems that had long-range correlations or write a dissertation on boreheads. So there's a trade-off. And where we're heading is to try to give these vague speculations some more mathematical and quantitative grounding. How good are models? Well, okay, maybe prediction error is good for that, but how big are models? Very often, there can be a set of data and competing models. So is there some way of determining which is better? Or we just have different schools of thought that argue back and forth? So can we put these questions on a more firm foundation? So that's the goal that we're going to pursue, and it guides what we're going to borrow from information theory. I'll talk a little bit about the technological uses of information theory, but we're mostly going to focus on information. And the main point I'm going to make over the next couple weeks is that there's not this unitary notion of information. We're going to start today and pretty much focus on and motivate things by information is uncertainty, but the sort of horizon is there are actually different kinds of information. There's information that's produced, there's information that's stored, there's information that's transmitted over space and time. There's information that is created and thrown away. There's information that's created by a system and stored and affects future behavior. So we're going to develop what I'd like to call now kind of intrinsic semantics of information. So that's the distant goal here. So we'll start simply today in the first couple chapters of Cover and Thomas. But these are some of the kind of the larger issues, just to, again, we're going to dive down and get kind of technical and more mathematical, but we'll come back up again, and the goal is to be able to frame some of these questions. And like I said before, we're going to end the quarter with a bit of a critique of this. Hopefully, you'll start to like these ideas and see there's some power in using information, being more precise, seeing the different kinds of information, and then we'll realize there are also limitations to that. And that will take us into the spring quarter where we talk explicitly about building models, extracting models from data directly, and comparing that back to these information measures. Okay, so main issue for the next little while is what is information? How do we measure unpredictability? That's certainly one thing we've been looking at, and we have now a nice detailed picture of these dynamical systems producing complicated orbits, and the Lyapunov exponents is some kind of measure of unpredictability. More puzzling, perhaps, is how do we say that one system is more structured than another? And can information theory help us with that? And also in the general kind of, at least the scientific setting, when you talk about information, it's sort of a puzzling thing because I've mentioned all these physical examples. Remember way back when, the mechanical pendulum. And so far, we haven't really talked about energy. But if you're a good physical scientist, presumably you want to talk about the different kinds of energy in a system and how they're stored and transduced into one kind or another. And there's this argument I made, remember that Honda ad, that there's kind of a fundamental difference between an energy description of a system and the sort of causal structure and contingency, which is sort of the role that information plays. So at least to start with, we're not going to, I'll just leave it as a question, that these two things, how these things are related, and they're not necessarily equal. There will be circumstances where they're sort of the same. For example, there's a lot of work in modern machine learning that likes to use energy concepts to describe how various learning algorithms work. In fact, it's just a metaphor. There's no energy there. What they do is they use a measure of information in the context of an energy. And if you try to give a physical interpretation of those systems, it's very confusing. So you have to be very careful about these things. Although, the analogy between information and energy is useful in that area of machine learning, but it's particularly problematic when you have a learning system that is a biological or physical system because it also has an energy story too. So I like to start at least from the framework, the setting where you have to argue that these things might be comparable. Right now, they're just different. Yeah, right. No, yeah. So I'd love to, at some point I keep asking if I can teach a course in the history of this, of information. It's really fascinating. There is a large, popular, semi-popular, popular book by the science writer Jim Glick called The Information. It came out about a year ago. It's like 600 or 700 pages long. It's this huge thing. I haven't gone through it yet. It slightly drives me crazy. Hi, Jim. But finally there's more actually overt appreciation of the role of information. We are, after all, in the information age, so what is it? But this is nice, interesting, very interesting, long history, and hopefully some historian of science will do it justice at some point. But one can treat this out in some detail, but just very coarsely, we start with the mathematical or physical theoretical foundations of thermodynamics with Boltzmann, talking about trying to understand the concept of entropy, in thermodynamic entropy, I should say, in large-scale, Avogadro's number molecule systems. And there he had this notion. The concept of entropy was actually introduced by Clausius as an important concept for describing the limitations on efficiency of heat engines. And the idea there was a measure that Boltzmann introduced, that the entropy was the number of microstates consistent with a given macrostate. So macrostate, I'll say this in a really simplified cartoon way, but a macrostate of an ideal gas is specified by various measurable parameters like pressure, temperature, volume, and so on. Once you specify those things, there of course can be just an unbelievably large number of molecular positions and velocities consistent with this macroscopic. And the realization was that this entropy measure was a key parameter in describing the quote, thermodynamic state, that the entropy itself was another one of these macroscopic parameters and was related to the number of microscopic states of a system. Well, then sort of comes along to kind of this communication systems, telegraph, telephone, the Second World War, and people were thinking about how you can communicate efficiently over physical devices like electrical wires. Also, how to hide information, cryptography. And so the sort of main sort of proponent of this was Claude Shannon. He was a colleague of an older mathematician, Norbert Wiener, and they had a kind of interesting sort of relationship, overlapped many workshops in the 40s and 50s. Shannon, in some way, sort of eclipsed Wiener in terms of the information theory that he introduced. He picked a simpler problem to work on. But there was this increasing appreciation that information played a role in human and biological systems, had something to do with when we control systems. Second World War, they wanted to make electrical devices that could use radar information to target and shoot down planes. As soon as they tried to do this, there are all these instabilities. Actually, they're chaotic. So there's a lot of interest in control design. And then Shannon in particular was working at Bell Labs, back in the 40s. And that's a company that was concerned about getting voice across wires. So he came up with this notion of information that we're going to talk about. As I said, it's absolutely critical, this notion. It affects everything we're doing at this instant. The very fact that we're webcasting down to Berkeley, the compression algorithms, the transferring files back and forth on the internet, it's amazing outgrowth of this very basic concept of information. And Shannon did a really important thing in this, which we'll come back and address. Shannon, part of paring down this vague question of what is information, he intentionally did not worry about what it meant. As you'll see, there's a measure of information, and he just was worried about the quantity of it. I have some telephone system. Can I characterize somehow what the maximum transmission rate of information is? Just quantitative. He doesn't care what you're saying during the phone conversation. It's just a quantitative measure, and that simplifies things greatly, although in decades following him, it was kind of a criticism, because when we use the word information, when I get some information, I'm not really interested in just getting information. I want it to be useful and meaningful to me. So that was kind of put aside, but mathematically, very clever thing to do, rather than get sort of stuck in the weeds of semantics and what does information mean. We'll come back to that. We'll talk about semantics. And there's a way to take his theory and add a semantics to it, as I suggested before. But anyway, the consequence of this kind of mid-20th century introduction of quantitative concept of information just had huge impact. So today, actively used in dynamical systems. The first way of distinguishing the degree of chaos in chaotic dynamical systems was Soviet mathematician Kolmogorov borrowing Shannon's information theory and bringing it into dynamical systems and using Shannon's source information rate as a measure of degree of chaos. Coding and statistics, mathematical modeling now, and learning, all have been affected by this, and it's only going to grow. It's growing quite rapidly. Okay, so what is it? We're going to start out thinking about information in the way Shannon introduces it. Like any sort of theoretical development, there's always hopefully a few pages in the paper where they're kind of give you the gist of what the idea is. And Shannon says, information is uncertainty. Right? So we observe something unexpected. There's a degree of surprise, and then the process of measurement, we gain information. Okay, there's kind of a duality in the use of words. There's a degree of surprise, which we're going to measure with a thing called entropy, and then because something's uncertain to us, then we have to measure it. We find out what state it is in, and then in the act of making the observation, we, the observer, have gained information. The more uncertain the system is, when we make a measurement, we're going to gain more information. My favorite definition is actually a fellow I was sort of a mentee of back down at UC Santa Cruz many years ago, Gregory Bates, an anthropologist. But part of this interesting crowd back in the 40s that got fascinated by information. People in neuroscience, people in sociology, anthropology, physical sciences, and so on. They're now starting to build digital computers, exactly how do physical devices process information. So his definition, probably the most concise one, is a difference that makes a difference. So up here, Shannon is sort of saying, well, differences. I'm surprised. There's a distinction. Bateson gives it a slightly more kind of functional flavor. It's a difference that has some effect or some difference. So Shannon's only kind of half the story here. But we'll come back to Bateson's definition and give it a quantitative grounding. Oh, I should say, so I kind of alluded to the social context of the 40s and 50s. So Shannon, Claude Shannon, Norbert Wiener, Gregory Bateson. It's an interesting period of time, maybe 1945 to about 1955, where there's this whole hubbub of make these devices do computing for you. Information, the idea that somehow these neurons that were spiking were processing information. There's actually a tissue in our bodies that was processing information. Its primary function was to process information. Norbert Wiener worked with a neurophysiologist for a number of years, and there was a famous set of experiments that came out of these people talking. And it was all sponsored by the Macy Corporation. The Macy Parade department store. Well, I guess the family was sufficiently enlightened. They had a series where bringing these very, very different people together. Turing, John von Neumann, mathematician, goes on and on and on. It's really fascinating to go back and look at some of the proceedings from these workshops that they did, sponsored by the Macy Foundation. There's a great book, and it's listed in the supplementary reading, called Dark Hero of the Information Age. And it's a biography of this fellow I just mentioned, Norbert Wiener, very eccentric mathematician, founded the math department at MIT. And it's a great read, and gives you a snapshot of this period, and also the personalities involved and difficulties. These ideas just didn't come immediately to Shannon's, mind. Wiener made, in some ways, was the biggest proponent of this new view. Made some very significant contributions, and it was just interesting to see. It was a period in time of intellectual life with a lot of cross-fertilization. In some ways, people say we're sort of in a kind of new time. Wiener called the endeavor cybernetics. So he coined the phrase cybernetics. So information and control and man and machine was kind of his theme, cybernetics. And with the rise of complex systems, state dynamical systems, people feel like we're going through another period like that now, studying networks, the dynamics of networks, generally now called complex systems. But there's been a revival of that same spirit. Okay, so much for the history lesson. Down to some definitions. How are we going to formalize this? Shannon just says, I declare, or I'm arguing in the first, in the preface, first few pages, that information is a measure of surprise, how uncertain. And it's sort of a kind of a historical slight joke. So Shannon was working with this at Bell Labs. He had this measure, and the John von Neumann, the mathematician, came in, and Shannon, the way the story is told, was puzzled about what to call this new quantity he had, which we'll introduce shortly. And von Neumann said, well, you should call it thermodynamic entropy. It has the same functional form as what was called Boltzmann's H function. And no one knows what entropy is in physics, and therefore you'll have a leg up in any discussion. So that's the story. Okay, so that's why it's called entropy. Von Neumann's kind of evil sense of humor, perhaps, but that's... And we will run into this confusion. So it's helpful and also unhelpful at different times when we're looking at analyzing a system in terms of information. Okay, so Shannon says, well, he's imagining we have some set of events described by some probability of occurring. And he says, the self-information of a particular event is the negative logarithm of the probability of the event. Okay, so, oh, it was sunny today. Well, that's kind of predictable, close to 1. I would have guessed that, or I would have looked online or looked at the forecast, and then when I woke up this morning, not been even remotely surprised. So that event had very high probability, or if I was certain about it, then so notice that his proposed functional form minus logarithm of 1, well, that's 0. So I'm not surprised. Okay, so this kind of works in that case. When the event is very predictable, I'm not surprised that his measure is 0. Okay. At the other extreme, we have something like a fair coin, or where we're completely uncertain as to what's going to happen tomorrow with the weather. So we imagine we have some set of events, heads, tails, whatever, and then he says that in that circumstance we have little prior prejudices about what's going to happen, no knowledge, the events can occur with equal probability, then this measure of surprise should be the largest. So plug that in. If we have some number of events, they're each going to occur with 1 over the number of probability uniformly. So minus log of that, well, that's just the log of the number of events. This turns out to be the maximum possible value that this proposed measure can take. And that's kind of the motivation. He goes on to add some more axioms, so we'll talk about those. But that was kind of the intuition, these kind of two extremes, and yeah, it kind of works. It should be 0 when things are predictable, and maximal when they're completely unpredictable. Right.
Not to get too off topic, but I just kind of noticed that it's interesting how it's in the form of a log.
Yeah.
Where it's
right.
Nice and addition and stuff.
Right.
As opposed to multiplication.
Right.
I'm wondering if there's
well, I can kind of motivate it a slightly different way. Many scales that we use are logarithmic. Also, many sensory modalities we have, right? Kind of we sort of hear sound amplitudes logarithmically. That's why we have the decibel sound. It's a logarithmic, power-based logarithmic scale. Earthquakes, of course, have very wide-ranging magnitudes, and so we have the Richter scale, which is also logarithmic, and it goes on and on. So, it's not unfamiliar to use a log. I have some observable here. He's saying, let's look at the probability of events. And that's also one move he's making here. He's saying we're gonna characterize the events, physical, biological things happening in terms of their probability. He's not saying, we're going to look at volts squared or current flow or something like that. I want to look at the probability of volts squared. So he's moving to a level of abstraction, just looking at probability distributions. And then the log, like I said, sometimes it's just sort of useful when you have a very, the thing you're looking at, the observable, has a huge range. It just helps compress the range. So that's a practical aspect of it. The interpretation he wants you to think about is this measure of uncertainty. So these are the two kind of motivating extremes. Okay, so he's proposing that somehow this measure of information or uncertainty is some function of the probability of events. But the question is, what is this functional form? He's proposed part of it. And we want to go from a set of events and a probability distribution over those events apply some function to that probability distribution, and get a number back, a real number back. So this is, we need some functional form. So here's how they set this up, and we get a concrete formula to work with. So we'll imagine we have some random variables, again, capital letters, or events, realizations that are finite in number, k of them. And then the random variables are described by the probability of each one of those events for them. You'll notice in Cover and Thomas, they use the shorthand notation. All of this can be summarized. The random variable x is distributed like p of x. Random variable y is distributed like q of x. Okay, so I like Khinchin's axioms. So what we need to do is write down some constraints on what this function f can be. So so the two motivating cases are at least two constraints on this, but that's not quite enough. So here are Khinchin's axioms for what is called the entropy. So the entropy, denoted h, of a random variable or its distribution is a function of its distribution. Okay? So here are the four axioms. So it's maximum at, well, equidistribution in the most uncertain case. At k events, they all occur with probably 1 over k. This thing should be a maximum. Or the other way to say it is that this number applied to a uniform distribution over the events should be the upper bound for any other distribution over the events. Okay? We'd also like it to be a continuous function of the parameters in the distribution of probabilities. As I vary each of the PIs, I'd like this number to behave well. I don't want it jumping around, so it should be continuous at least. Now things get a little more formal, sort of feel like they're doing this to solve a math problem here. Expansibility. So this function of k events should be the same as a function of k plus 1 events when the new event I've added never occurs. Technically, this is a boundary condition on a functional equation. But, and then finally, although this is an important kind of interpretation, when I have pairs of events, so now I have a joint distribution over x and y. That's a distribution, and I can apply this mysterious h function to it. When the two variables are independent, I want the joint uncertainty, the uncertainty of events occurring together, to be the sum of the individual. So there's kind of a decomposability. If I have a big system, but the components of it are behaving independently, then the entropy of the whole thing will be the sum of the entropies of the individual components because they're not interacting. Okay. So, and this is important because we're going to start asking questions about the relationships between random variables. So here's a little hint of how this information measure could maybe indicate that there are components in the system. We'll look for those pieces that are statistically independent. And here, if we can figure out what this h should be, we would have a quantitative way of, just with scalar numbers, not comparing the distributions, but just single numbers. Scalar number, saying that components were independent. Okay, so axioms, and then magic happens. So theorem. Given those four axioms, there is a unique, up to some proportionality constant, functional form for this h function. And it is this, now called the Shannon entropy, or sometimes the Shannon-Boltzmann entropy. So the entropy is the sum over all the events of probably each event, log probably of each event. And there's a minus sign here. In other words, it's the average self-information. So we just say p log p, kind of like, it's almost like a token. It's a p log p function. So we'll explore what this tells us about a random variable and extend it to deal with collections.
Is it true if we, does it have to be discrete?
Correct. Yes, so it could be that the event space was continuous, and then you end up with an integral here,
Right.
and then it gets up trickier. Some of the properties I'm going to talk about today don't hold in the continuous case. There is, once we get through this, then like 3 or 4 lectures, you might just, to assuage your curiosity, jump ahead in Cover and Thomas, and there's a chapter on differential entropy, and you can see what some of the differences are. So yes, you can do this for continuous random variables. Yeah. Absolutely. Just it's simpler in the discrete event case, much simpler. Okay, so Shannon had a different set of axioms. And these are usually the ones he had, the fair coin distribution, maximum entropy of 1, continuous function, same as Khinchin. And then he had this merging property, which I can force myself to make an interpretation of, but it's not as intuitive as, say, the independence, say, axiom of Khinchin. Here, if I have k events and I group events 1 and 2 into a new compound event, I have now a distribution over k minus 1 events, and then the entropy over k of them is this reduced smaller distribution plus this extra correction over a binary variable, essentially. Did event 1 or event 2 occur? I can't say much more. Doesn't like roll off my tongue to give this an interpretation. So, but that's what he assumed, and same thing. So those are constraints, and you're trying to find some mapping from distributions to real numbers, and there's it's called a functional equation you have to solve. You get the same p log p function. So now notice that this is just a proportionality. Solving finding the function that's consistent with the axioms in either case, the Shannon or Khinchin case, it doesn't tell you exactly. It's not an equality, it's just proportional. This is the functional form. But we're going to fix that. You'll see in just a second. Right now. What we're going to do is choose a base of the logarithm, base 2. That has consequences. So this will be the definition we're working with, that the entropy of some random variable x is equal to minus some p log p over the events. Logarithm base 2. You might wonder about zero probability events. Well, if you do your L'Hopital's rule, you can convince yourself that 0 log 0 is 0, so it's okay. And if I do rewrite it in kind of physicsy notation, it really is just going back to Shannon's original argument about individual events having self-information. It's just the average self-information, average over the event probabilities. Now, choosing the base 2 here has a vocabulary consequence. We choose the log base 2, the units of h are in so-called bits. These are binary digits. And you'll see why. We'll go through a couple examples of why base 2 is kind of helpful. It's related to this game of 20 questions. In some circumstances, in particular with the continuous random variables, it's often the case that you use log with a natural log, base log base e, and then the units are called mats. We'll use bits. We'll use base 2. Okay, so what are the properties of this h of x function? Well, and Cover and Thomas go through this. We won't, but it's never negative. If the entropy of the random variable is 0, then there's for only one event, the probability is 1. And recovering sort of axiom. When we have a uniform distribution, the k events occur with probably 1 over k, then h of x is log base 2 of k. The entropy in this case is roughly just counting the events. Okay. So some other things. I guess you might think of this as an example. If we had a binary random variable, 0s and 1s, and it's a bias coin, so I parameterize the bias with little p here. Probability 1 is p, probability 0 is 1 minus p. I can just plug that distribution in, of course, and that's what the sum expands out to. I've got 2 events, so there's 2 terms in the sum, and I get this function. Well, here's what it looks like, just to plot it out. It's this Humpy type of function. 0 to 1 actually goes up 0 to 1. There's a lot we can read off of this. So in the fair coin, that would be 50-50 here. Fair coin, you have the maximum value of 1 bit. So 1 bit per flip. Completely biased coin, it's 0. So that's either 0s all the time or 1s all the time. Doesn't matter. It's 0 when it's completely biased. And this is good to keep in mind because we'll be working with more complicated distributions, but one of the reasons this function just mathematically is useful is what we're seeing here, this convex property. I could have many, many events. And this h function, as I vary the probabilities of the events, get back to that continuity axiom, is this nice smooth function. So for example, we might want to maximize it at some point, so we can do some hill climbing. So convexity is a really important property of this. Remember, what we're doing is we're going from a distribution which has many parameters down to a scalar number. And part of the trick here is that this h function captures a lot of the structure in the distribution. So you'll see it's very useful. Rather than having to carry on bags of probability numbers, probability amplitudes, we can get a scalar out. So so here's another example, help us interpret what this means. Imagine we have an IID process over 4 events, A, B, C, D, and they're given with this distribution. A occurs with probability half, B 1/4, C and D with probability 1/8. Okay, I give you the distribution, and you go write your little Python function to calculate P log P over that, right? That's just a formula now. We just plug in a distribution, we get a number back, and we get 7/4 bits. Well, so what? What's the number mean? So here's how to think about this. So what Shannon pointed out was we can think about this number, this entropy number, as the average number of questions you have to ask during an experiment with this random variable to figure out which event occurred. If you ask the questions optimally. Okay, so we've got this thing, it's IID, so there's no temporal relationship between various queries of the experiment. We just get these reports back, A, B, C, D, A, B, whatever. Okay, so how are we going to ask a question? We're going to play this game of 20 questions with this event random variable. Well, okay, I have to ask one question. So no matter what, I have to ask one question. So what I'm going to ask, first off, is the event A? And the answer will be either yes or no. If it's yes, I'm done. But half the time, it's going to be no. And what's that telling me? It's telling me it's B, C, or D. So I ask another question. I choose, in this case, to ask, is it B? So what's going to happen then? Right? So up here, when I said, is it A, I'm breaking the set of 4 events into 2 subsets with 1 event and 3 events. And the probability between those 2 events is 50-50. Okay, but now I know it's not B, so now I'm looking at this 3 event set. I have a sort of non-normalized distribution. If I normalize it, then ask, oh, is it B? Same thing happens again. I'm breaking the 3 event set into a set, 2 subsets, one with 1 event and one with 2 events. And it turns out, because I asked if it's B, it's actually a 50-50 question, and so on. So you can sort of tree out. I have to ask one question. I will ask one question with probability 1. If it says no, it's not A, I have to ask another question, but that's only going to occur with probability half. And then so on, the rest of the set. I'll ask a final question, is it C, a quarter of the time? And notice that when you sum that up, that is 1 3/4. So that's nice. I mean, I just give you a distribution, the scalar number comes back, and you at least have a little hint about this query exercise to find out for a particular event. Yeah?
So I guess while we are calculating the average number, those probabilities are the probability of asking the question.
Right. So doing this many, many times. Right. So, yeah. So think of repeated experiments and averaging. Sometimes I ask 1 question, sometimes 2, sometimes 3, sometimes 1. Okay. So Shannon says, actually, this number here is the optimal. If I ask the questions optimally, which we have to deal with, then the average number of questions with an optimal query will be the entropy. So we need to think about this a little bit. So I just would now give you some graphical form for what I just was arguing. So we just calculated this out. And so first I asked, so this is some kind of decision tree. I have these 4 events confronting me. The event happens and someone is holding it and I'm asking them questions. So is it A? Well, A, that's going to happen half the time. Or not A, which is, was it B, C, or D? That'll happen half the time. Now at that point I have 3 events left. Now I'm grouping it into B and not B. So D and not D, notice that those, if I normalize them, that would be 50-50. It's the same weight here. So again, those probability that's going to be B, given that it was not A, probably that's going to be B happens half the time. And then I'm going to have to ask another question half the time. And then I say, is it C? In either case, if it's C, that'll happen half the time. And not C, well, I already know it's D, so I'm done. So that's basically a kind of decision tree explanation for how we're summing things up here. Now, it also helps when we lay out our question asking strategy so explicitly. What happens if I was being perverse and asked it in a different way? Okay, so the perverse way, of course, is to ask about D. I mean, you already have the intuition here. So, okay, so my first question, is it D? Well, what I'm doing now is I'm breaking the 4 events into a set with 1, but the subset with 1 event occurs only 1/8 of the time. So 7/8 of the time, I'm going to be wrong. So I'm going to ask one question and be right just 1/8 of the time, but I have to go on, and that's going to happen 7/8 of the time. Not so great, right? So then what do I ask? Oh, C, okay. Well, now that I've gotten rid of D, I'm over here, it's not D, I have a new distribution over ABC, and I renormalize it with, this is gone, I sum this up and it's divided through. So I have this new distribution here, and from that you can see that if I ask C, well, I'm doing the same silly thing before. I'm picking a subset that has the least likely event. So this is going to occur I'll be right 1/7 of the time and wrong 6/7 of the time. In other words, I'll have to ask another question. And then finally I can ask, is it B? And same thing. I now have 2 events with this unequal distribution. Yeah, so 2/3 of the time it'll be A, 1/3 of the time it'll be B. And then sum that up. So we have one question always, another second question 7/8 of the time, a third question 6/7 of the time. It's 2.7 questions. Clearly longer. It was not an optimal strategy. So if that's my decision approach, I'll be spending a lot of extra effort querying. Okay. So notice that under the optimal strategy, at each stage, I looked at the distribution I had left, and I tried to choose sets, to ask my question, sort of cleave the sets into the most even distribution. I'm free to choose what the subsets are, and I cleave it so it is close to 50-50 as possible. Why? Because that's the maximum. Well, the variable looks most random to me, therefore the answer to the question is most informative. Right? So you're trying to choose partitions, should sound a little bit familiar, so there will be a connection, so that the event space is cleaved sort of to give what's left over the most random looking distribution, because then the measurements, the actual outcomes, will be most informative. So Shannon shows that this entropy, again, it's just a function now, just a formula. Distribution, you plug it in, you get a number out, and you're going, oh, well, that's interesting. It should be the decision strategy. It's sort of the performance of the optimal decision strategy. It's not telling you what the strategy is. You would have to figure that out yourself. And that's actually the whole area of coding theory, is what are optimal ways of cleaving these things up with the fewest number of questions. In the arena of coding, which we'll get into, the fewest number of questions are the number of bits for compressing a random variable. So we want to be close to this optimum. And this is one of the main reasons Shannon's information theories had such a huge technological impact. Just this idea that, well, we'll talk about compression. It helps indicate how we can compress. Okay, so what kind of interpretation do we have of this p log p function? I guess I sort of argued its degree of surprise in a random variable, our uncertainty. Sometimes you'll see it used, sometimes in the theory of computational complexity, as the information required to describe a random variable. It's all just different vocabulary here. There's also this interpretation, which, forget all this other stuff. It's just the most practical interpretation. It tells you how flat the probability distribution is. If it's peaked, the number is very small, and this H number is large when it's flattest. That's it. I mean, just that. It also has this nice convex property, and those two properties together are going to give us a lot of leverage in analyzing structure and probability distributions. Just the fact. So maybe different applications. One other of these vocabularies is more useful, but mathematically it's just flatness of a distribution. No great mystery, actually. Okay, so now, so that's the main function, and what we're going to do is sort of explore that. Now, what we're going to try to do is extend this to deal with multiple variables and see essentially what these extensions allow us to say about many-way probability distributions and how they're organized. Okay, so we'll talk about first just two random variables. So using the Covert-Thomas notation, I have this pair of random variables x and y, and they're distributed with this joint distribution. Okay, and well, I can either think of this as one random variable that is the occurrence of x and y events, or it's two random variables, your choice. But I just have a distribution, and I can just plug it into the formula. So we have the joint entropy. It's the uncertainty in the occurrence of pairs of events. And I just plug in the distribution into the minus some p log p formula. I'm summing over all possible pairs of events, weighting them by the joint probability, but it's still the minus log probability of this compound event formula. And you can show, with this this really is just a minor extension, just plugging in a joint distribution into the previous single variable formula. You can show that this joint entropy, when the random variables are independent, this joint entropy is simply the sum of the marginal entropies of the individual random variables. Now here, I want you to notice something. We're going to shift over, so we're almost always talking about simple formulas and expressions and identities like this, the information level, right? And these are sort of equivalences and inequalities over scalar numbers. Right? So we're not having to deal with the distribution. But the form of these identities, information identities, really just has to do with how you can factor joint distributions into marginals, how you make marginal distribution from joint distributions, how you make joint distributions into conditional distributions. So there's almost a parallel, there is a parallel development. I can work with probability distributions and have products of distributions, or I'll have sums, because of the log, over these scalar numbers. So that's, when you're, some of the exercises become proving some things. That's really all you do. Sort of, you go up, do your probability theory factoring for your three-way joint distribution. Maybe you have to be a little bit clever, and then you take P log P again, and pop back down to here, and then you have this identity over scalar numbers, these uncertainties. Okay, conditional entropy. So this will be the average uncertainty in one variable x when I know what happened with another variable y. That's denoted this way, x bar y, the uncertainty in x, given that I know y. And then we average that over all y events too. So it's just, again, same p log p form, except I now plug in this conditional distribution. So this is a kind of a conditional self-information. And then I average over the joint probability of pairs of events. Again, through these information identities, going back up to how you factor joint distributions to conditional distributions, you can show that you can basically define the conditional entropy this way in terms of the difference between the joint distribution and the marginal of the variable you're conditioning on. So uncertainty in x given y is the joint uncertainty minus the uncertainty in y. Kind of factoring out. So here you should think, oh, everything in y is kind of specified, but it actually didn't determine all of x. There's a little bit of randomness in x left over once I fixed y and the joint events. It'll kind of make sense if I have, this great uncertainty in pairs of events. I can just factor out the kind of novelty that y is introduced. And the difference is this residual uncertainty in x. This is not symmetric. So these numbers, the uncertainty in x given y is not the uncertainty in y given x. It's not a symmetric function. Right, so again, to calculate these, we need to start with this joint distribution. So here's an example. I mean, if you're an undergrad trapped on campus in one of the dorms, you go very periodically, very regularly to the cafeteria. And so, of course, it's the case that the food served at the cafeteria is random variables, right? They're random variables. Lunch, dinner, breakfast, whatever. You never know. So the random variables we're going to talk about is dinner, one night, and then lunch the next day. And in this dorm, basically, there are only two choices. You either get pizza or meat with vegetable for dinner. I'll denote those particular events, P and M. Or the lunch the next day is either casserole or a hot dog, or C and H. Okay, so you go, the quarter wears on, and you've got a pretty good estimate of how often you get pizza, how often you get meat with vegetable, how often you had lunch, casserole, or a hot dog for lunch. And so here's some example numbers from one cafeteria on campus who will go unnamed. Well, okay, so here's a distribution, and we can certainly just apply this to in the setting. So we can calculate our uncertainty, and what we're going to have for dinner. Well, it was 50-50, so it kind of makes sense. It'd be one bit. You really don't know when you show up for dinner. However, the uncertainty in lunch is a biased coin. It's 3/4, 1/4. Typically, you get the casserole. So there, that's the binary entropy function, the hump function I showed you before, at the parameter bias of 3/4, and that's about 0.8 bits. Okay, so lunch is more predictable. Dinner is completely unpredictable. However, you also notice the pairwise events, what you had for dinner the night before and what you're having for lunch today. And you notice the co-occurrence of those things, and you kept running a table of these things. So here's what the unfortunate student realized, that pizza and casserole, pizza for dinner, casserole for lunch, for 1/4 of the time, pizza, hot dog 1/4, meat with vegetable and casserole half the time, and then you never had meat with casserole and hot dog the next day. Okay, so something's going on. Maybe there's some sort of correlation here. Well, first, just the exercise is to convince yourself that with this joint distribution over dinner and lunch, that there's 1.5 bits of uncertainty in the pair of events. Okay, let's just plug in the numbers and chug. And you can also immediately conclude that the dinner random variable, the lunch random variable, they're not independent, right? We had this condition for independence, that the joint was the sum of the marginals. Well, we just calculated the joint. That's 1.5 bits. In the previous slides, we calculated 1 bit for dinner and 0.8 bits for lunch. That's 1.8 bits. Those numbers aren't the same. Therefore, lunch and dinner are correlated. Okay, that's useful. The question is what? Well, okay, so I've introduced some things, and we can kind of probe around here. You might think the conditional entropies. What's my uncertainty of this given that? Okay, so I can go through and calculate. I have the joint distribution, so I can kind of massage it in different ways and calculate these different entropies. So let's go through and calculate. I won't talk through the whole thing, but you can calculate from the joint distribution what the uncertainty in casserole for lunch is, given that you had pizza the night before, right? And that's just the ratio of pizza casserole as a pair occurring over the probability of pizza and so on. So you can kind of work through on your own that you get these conditional probabilities, and then I can calculate. I'm suspicious. I want to know, if I know I had pizza the night before, what can I predict about lunch? How uncertain am I about lunch the next day? Well, it's pretty clear that pizza the night before, casserole, hot dog, 50-50. Not useful at all. It's not, having pizza is not predictive. However, if I have meat with vegetable, it actually is completely predictive of what I'm going to have. If I have meat with vegetable, I'm going to get the casserole for lunch. So, the conditional entropy, given the particular event of meat with vegetable, the lunch is completely predictable. We have 0 uncertainty. Okay. And we, of course, could average this the way the formula was before. So there's an average uncertainty of 0.5 bit. Uncertainty, if I know what dinner was, my uncertainty about lunch is 0.5 bit. Okay, and you can turn this around. Again, we're trying to understand, now this would be slightly acausal, rather than thinking about dinner the night before and lunch the next day. I can ask the other way, right? Maybe there's some reverse causality. It doesn't make sense physically, but this distribution might have come from something else. We wouldn't even know that there was a temporal relationship to these things. So you can calculate the other way. If I know what I'm having for lunch the next day, I can ask what's the relationship with what I had for dinner the previous night. Okay, work through this. And again, here, well, if I casserole, that's kind of a biased coin. It's slightly informative, but having hot dog the next day is completely predictive that you had pizza the the night before, and we can calculate the, given that I know that I had casserole, what's my uncertainty in the dinner? That's h of 2/3. This up here, it's about 0.9 bits. And then hot dog, well, it's completely deterministic. I'm going to have pizza, so there's 0 uncertainty. So we calculate out the sort of average, the average conditional uncertainty in dinner given lunch, and it's about 0.7 bits. Remember the previous calculation, this uncertainty dinner given lunch is not the same thing as lunch given dinner. In fact, this is a bit higher, the uncertainty in dinner given lunch is a bit higher. Maybe that indicates that there was some temporal causality in this. Okay, so now on to some more definitions. I need to introduce a few more things so we can start talking more directly about what structures in that cafeteria distribution. So let's think about two random variables, x and y, that have different distributions, p and q, but they share a common event space. So there are a couple questions about how do these two different random variables relate to one another. And the first sort of piece of that is something called the relative entropy, and it's denoted this way: this sort of script d x double bar y. So it's the relative entropy between x and y. And it has this expression: the average over the probability of events under the p distribution, the ratio of probability of x under the p distribution and the probability of x under the q distribution. So same event space, we have these two different distributions, and we're kind of going kind of event-wise and comparing them and looking at the ratio of the probabilities. You have to worry about these conditions, of course. In extreme cases, it's still 0 log 0 is 0, so that's okay. But this relative entropy technically is sort of useless when the q distribution assigns 0 probability. In other words, the distance between the relative difference between the x and y random variables would be arbitrarily large. So typically this gets used in situations where we have a common event space and all the events have positive probability. Okay. So typically it's applied to, in the case where the q distribution, all the events have positive probability. So sometimes instead of putting the random variables in, sometimes we'll put the distributions in. You see it in the literature a couple different ways. Properties. So this relative entropy is never negative. When it's 0, the two distributions are the same. So that's why it's useful comparing things. But it's not symmetric. So that kind of messes things up for us if we really wanted to look at a difference between two distributions. Nonetheless, it's very, very useful when you compare two distributions, principally because you only have to use the marginal distributions of the variables. I don't have to know the joint distribution. I'm just kind of pairwise comparing the probability amplitudes. That's it. This is often called the Kovach-Leibler distance, sometimes divergence, but that's slight misuse. Information gain, the number of bits of describing y as if it was x. So sometimes if you're trying to describe an information source, but you have the wrong model, the relative entropy, you kind of imagine your model giving one distribution, but the true distribution is something else. This information gain, or relative entropy, is useful as a measure of error in the description. And discrimination is often used. Two things going on, and how can I discern between them? I have two bias coins, different biases. How can I give an informational measure of their difference? Now the problem is, despite this sometimes use of the word distance, it's not really a distance. First of all, it's not symmetric, and it doesn't, more importantly, it doesn't satisfy any kind of triangle inequality. So it kind of fails in helping us bring some kind of geometry to the space of distributions. But useful, again. For calculations, you don't need the joint distribution, so that's very handy. When you can use it, it's good. Now, a related quantity, in many ways much more fundamental, is this concept of shared or common information between two random variables. So again, we have two random variables. Now we're going to assume we have a joint distribution between them. And Shannon introduces something called the mutual information. And it's denoted x semicolon y. some of us are now using colons here, but you'll see in Coverton it's a semicolon for historical reasons. And it's the information gain between the joint distribution and the product of the marginals. Kind of, again, if you incorrectly wanted to think of a distance because we're using the information gain, this would be like the distance between the distribution and its product of its marginals. In other words, it'd be a measure of independence. Right? If x and y are independent, then they're going to factor into this product, and then these would be the same distribution, and d would be 0. Okay, so it's a measure of dependence. Or just to try to write it out more directly, not in terms of information gain. It's the average over the joint events of log of the ratio of the joint distribution to the marginals. And it has a number of useful properties, which you can kind of see from here. So first of all, for two random variables, it's never negative. It's symmetric. Right? The formula doesn't matter what slot in the joint distribution I put x and y in. Appealing to our knowledge of how to factor the joint distribution in that definition into the product of a conditional and a marginal and so on. You get different identities, so here are a couple of them. So this mutual information between x and y, it's the uncertainty in x minus the uncertainty in x given y. So there's a certain amount of information in x, except there's some of that that's explained by y. What's left over is what's shared between them, right? This term here is the uncertainty in x left over once I know y. And I'm going to subtract that out of the sort of information that's in x. So that's the shared. Right? There's a symmetric version of this. I could have had y here, and then y given x. A number of different ways to express this. The sum of the marginals minus the joint. And if you ponder these, it's a nice exercise in kind of, contemplation to go through these expressions and try to make sense of different identities. The mutual information of a random variable with itself is the entropy of the random variable. That's kind of interesting. Actually, mutual information has some nice mathematical properties so that people actually take this as an axiomatic development of information theory. They start with mutual information and then define an uncertainty. And then, very importantly, when the random variables are independent, the joint factors in the marginals, this mutual information is 0. So it's a measure of dependence. It's 0 when they're independent, and there's large when there's some dependence between them. So, information one variable has about another, information shared between two variables, measure of dependence. So they're different interpretations, slightly different interpretations. Well, both the relative entropy and the mutual information are, we think they might be useful tools when we get back to talking about eating, or eating examples. Okay? Right? Because we're trying to understand the dinner random variable, lunch random variable, so we can just calculate these numbers out and see if they're useful. So what's the mutual information, shared information between dinner and lunch? Well, because of those identities, there are different ways I can calculate I. So I choose this particular one. Sometimes when you're doing the problems, there are other identities that are more useful because they're easier to calculate in terms of what's given. So here, the uncertainty in lunch minus the uncertainty in lunch given dinner. We calculate all those numbers out before. So it's about 0.3 bits. So there's something about, the event of having pizza and meat and hot dog and casserole that's shared. There's something shared in all that. Then we saw some hints of that already, of course. So in this form, this particular identity, we can think about this as the reduction in uncertainty about lunch, given that we had dinner. Nothing else said, I'm that uncertain about lunch. But I reduce that uncertainty because I know something about dinner. Right? But there's still some residual uncertainty, which then I factor out with the uncertainty of lunch, and what's left over is the information. The other way around, I can expand this in a different way. The uncertainty in dinner minus the uncertainty in dinner given lunch, so let's work that out. Different particular numbers, but lo and behold, it's the same. Just demonstrating numerically that it's symmetric in the two random variables. You can permute those. So we have about 0.3 bits shared between dinner and lunch. But the sort of burning question is, what is the shared information? So as the story goes, you make an inquiry. So it turns out that the vegetable that was served at dinner, when you had meat and vegetable, that's actually used to make the casserole the next day. At least that's what the chef said. So you can also try to calculate this relative entropy. It's slightly more awkward, but it helps illustrate actually what we often do in using it. So this information gain of relative entropy, we have two random variables and they have different event spaces. So how are they really comparable? So in this little narrative, I can kind of concoct a relationship. You often have to find, if you want to compare distributions over different kinds of events, some relationship between the events themselves. So we have pizza, meat, casserole, hot dog. Those are different things. But in the story, we'll just say, oh, it turns out that in each case, one of them is vegetarian and one of them is non-vegetarian. So that now becomes the common event space, vegetarian, non-vegetarian. So now I can compare the two distributions, the marginal distributions of just dinner and just over lunch together in that relative entropy formula, where I'm using the vegetarian, non-vegetarian events to compare the probabilities. And you can calculate out, so the relative entropy of dinner given lunch is about 2 bits, lunch given dinner slightly smaller. Okay, that's just kind of a numerical exercise here. So let's move on, except for one little comment, two slides. So I've been kind of criticizing the relative entropy for not being a distance. Well, it turns out that there actually is a distance in the space of distributions. This can be very useful. This assumes knowing the joint distribution between the two random variables. And you can show that, this is called the information distance, little d, x and y. If you sum the the conditional distribution, uncertainty in x given y plus the uncertainty in y given x, that is actually a distance. You can also kind of rewrite it. It's the difference between the joint, the total uncertainty, and the shared information. Right? That difference is the information that is not shared. Total available information, total uncertainty, minus that which shared. This is what's not shared between. Now you can that sounds a little bit like symmetric set difference. It's like that basically leads to this being a metric. So the way to think about this, I have to introduce another random variable z here to say what the properties are. It's never negative. Well, that's good for when x and y are the same distribution, it's 0. So at the same point in the space of distributions, it's symmetric. It's kind of important. Distance from here to here, from here to here, and backwards is the same. Sort of more subtly, it actually satisfies a triangle inequality. The distance between x and y is less than or equal to the distance between x and some new random variable, some other point out here, plus the distance between z and y. And it also has a sort of independence threshold. It's bounded above the largest distance you can have is when the two distributions are independent. So, very nice properties. And so it is actually a distance measure in the space of distributions. Oddly enough, it's not used that often, partly because you have to know this joint distribution. So it's often harder to calculate, but at least in sort of more recently in sort of more advanced forms of statistical learning theory, people are starting to use these metric properties of the space of distributions. And we can calculate it if we like. We already calculated these two conditional uncertainties, and so we can calculate the distance out. It's about 1.2 bits. There's quite a bit of randomness that's not shared between having dinner and having lunch. Okay, so that's a lot of definitions, but it turns out it's actually quite organized. So sort of calculationally, we're sort of trying to understand this entropy formula, H thing. It's a function of distribution, so very often when we prove properties about this scalar quantity, we unpack things in terms of distributions, do our factoring a joint distribution into conditional probabilities, and then repack things. But after you do that for a while, you realize you can actually just start working at the level of these information measures and leave kind of the distributions behind. So there's quite a bit of structure to these information quantities. In fact, I'll probably be slipping more and more into saying information measures. Here's a graphical summary of everything I just introduced. And these quantities are closely related. So imagine that this somehow is the event space for random variable x. And its size is going to be given by the uncertainty in x. And now I have another random variable y, yellow, and then the size of its circle is h of y. In fact, I probably should have drawn these different sizes. So what's the joint entropy? The whole thing, the total area. Right? I don't count the overlap twice, but just watch, just this area. So it's just three pieces. This yellow crescent, this red crescent, and the shared orange piece. Those are the terms in here. And I can also immediately start reading off some of these identities I was just going through with this. It's my total uncertainty in x. But then I hack out the y piece, so this red crescent here is the uncertainty in x, given that I knew y. And symmetrically, so uncertainty in y, I hack out the x piece because that's given, and that happened, and that's this yellow crescent is the conditional entropy of y given x. So information theory has a very close relationship to the set theoretic organization, kind of Venn diagram organization of the event spaces. The middle wedge, well, that's the shared information. And remember, I just said the distance was the difference between the joint, and I subtracted off the mutual information. Well, what would that leave? That would leave the outer wedges, the outer crescents. And that is, in fact, the information distance. So this is the other benefit of using information theory. These quantities, they have these kind of tight relationship with each other. You kind of move around, read off all the quantities. We are going to use this Venn diagram and extend it to multiple variables. And it's going to be absolutely critical for figuring out what it means for 3 random variables and 4 random variables to share information. In fact, the algebra that you would do and factoring of probability distributions, these calculations explode on you when you go to more than 2 random variables. Very tedious, but there's some very simple diagrams that help guide you through the calculations. So, in fact, it turns out that these h and I, we just refer to them now as information measures, and they actually form something called a assigned measure over the space of events. So there's a lot of mathematical structure here. Right now, we can just think of this as a nice tableau for what seemed like a long list of definitions. In fact, they're all closely related to each other. So it's a good thing to kind of keep in the back of your mind and get familiar with the set theoretic organization. And they're also just, kind of just to finish up, to point out a couple results in Covert and Thomas that are useful, that will be useful. I keep talking about multiple random variables. Well, we've already been dealing with multiple random variables when we look at time series, right? So the goal here is to actually introduce information theory and now extend it to deal with time series over this bi-infinite chain of random variables. That's an infinite number of random variables. So we need to think about multiple random variables. So here are a couple. I'm just pulling out a couple of the various rules of manipulating these entropies and mutual informations that we'll use. So right offhand, they're just kind of hanging out there as mathematical results, but they will become useful. So you can take a joint distribution over n random variables and factor it into this sort of telescoping product, a sum, pick one variable, say 1, and then uncertainty of that plus the uncertainty in the next variable, given that you do the previous one, and so on. So kind of telescopic conditioning on more and more and more. But just different ways, systematic ways of expanding a large joint distribution. You can imagine if this was a time series, this might be useful. There are also conditional mutual informations, and this is going to be important for how we think about the kind of causal structure, kind of codependence between random variables. You can ask, oh, okay, what's the shared information between x and y, given that I know some other information? And sometimes things look like they're correlated, but that can be not the case. You use something else. And then the formula for it is pretty easy. Here, this is a previous information identity we had before if I wasn't conditioning on Z. Basically, the conditioning just carries over. It's sort of a rule here. When you condition and then you factor in some other expression, whatever you're conditioning, it carries over to all the other entropy terms. And then there's a chain rule. So if I have a group of random variables, n random variables, and I want to know how much information they shared with some other random variable y, there's an expansion, kind of like the previous, it uses the previous entropy chain rule to factor that out. So sometimes, if you're in a time series, things are decaying, you can chop off one of these expansions because the terms get smaller and smaller. Cover and Thomas they list this sort of quickly, but useful technique. That's what I'm sort of calling them out. There's conditional relative entropy. Okay, so I can have the relative entropy between two conditional distributions. Nothing, it's completely straightforward. I'm just plugging in for P and Q, conditional distributions here. And there's a little chain rule of how you can take the relative entropy between two joint distributions, kind of break that out into the relative entropy between the marginals and then the conditionals. Again, it's just factoring a joint distribution into a product of a marginal and a conditional. Also useful sometimes. Other properties. Well, we've already kind of talked about this one. X is uniformly distributed. The events occur with equal probability. The entropy is just log of the event space size. Sometimes you're just interested in how many active events are there. You've got some giant distribution. I just want to know how many events there are. Calculate, this P log P formula. No, it's about 7 bits. Okay, well, I'm doing base 2, 7 bits, then it's something like 2 to the 7 distinct events are kind of active for having probability. It's just a real quick kind of use of this. This counting events, log of the event space size, is always the upper bound of the entropy rate. In fact, there's a way of sort of rewriting the entropy in terms of log of the counts minus this information gain between the distribution you're looking at and a uniform distribution. Another property, we argue, this often gets used in arguments. We will use this in arguments later on. Nice way to remember it is conditioning reduces entropy. Right? So if I have some uncertainty random variable, I tell you something else, your uncertainty can't go up. It goes down. Right? So, and in general, there's this independence bound. Right? The joint entropy is always less than the sum of the marginals. That's often used in approximations. I don't know what's going on in this collection of random variables, but at least for the question I'm interested in, I'll just assume they're independent and get this back and move on. Yeah, so we'll use some of these things in arguments later on when talking about different measures of information and causal models. It's part of what we're trying to do is develop these tools, hopefully just scalar numbers, not working with full distributions, that tell us how variables are related to one another. So there's a really helpful notion of a Markov chain. So now imagine we have 3 random variables. We know their joint distribution. We say that the 3 random variables are a Markov chain. Let's know that x goes to y goes to z when the uncertainty, the probability of x and z occurring given y factors into this product of marginal conditional distributions. Right? If I wasn't conditioning here, this would just look like a statement of independence between x and z, right? But now I'm conditioning on that. So I get this factoring of this joint distribution over x and z, given that I knew this variable y. So condition on knowing that the joint distribution factors. Or the other way to say it, maybe more concisely, is that the shared information between x and z is 0 given y. So the way we say this is that when we have this relationship between 3 random variables, we say that the y variable shields z from x. Whatever dependence there was, it breaks it. And then we denote that this way. conditioned on y, x and z are independent. It's symmetric. Y shields z from x, it shields x from z. If in this chain, so I have two random variables, but the third one is a function of y, then I'll also have a Markov chain, which seemed kind of contrived except for one interesting and often used property called the data processing inequality. So if I have a Markov chain, x goes to y goes to z, the information that's shared between x and y is greater than the information shared between the variables at the end of the chain, x and z. Or the other way to think about it is if I have this third variable z that's some function of y, then the mutual information between x and y is always larger than x and any kind of processing, g, you could have done to y. In other words, I can't do some fancy thing, this function g, to the variable y and get more information out than I had already in x. That's the data processing. You can't increase information by manipulating and processing or anything. I mean, notationally kind of simple, the interpretation is rather interesting. Okay, well, and just to finish it up. So, the hidden variable in our cafeteria story was this other thing, leftovers. If somebody had come to you and said, leftovers, that's it, that's the secret. Then, in fact, given that information, then lunch and dinner would have been independent, because that was what was being transmitted. So we had a Markov chain. So the whole story was a Markov chain. Dinner, this hidden variable, leftovers, shielded lunch from dinner. And that's exactly the kind of discovery, and it's a little kind of contrived example, but it exactly illustrates the kind of discovery we want to do. If I give you some joint distribution, the exercise is try to find how you can factor this into components, and maybe those components have some interesting physical, biological relevance. So we're moving in the direction, and we want to automate this as much as possible. First of all, we're simplifying things. We're using scalar numbers now, not whole distributions, and figure out how they factor. We can use these numbers to give us a hint about what an interesting decomposition of what appears to be a big joint process is. So, well, good. So that's it. So this is the first chapter 2 of Cover and Thomas, kind of selectively presented with some tools we'll need later on. And then we're going to jump ahead to a couple later chapters and just read these particular sections in 5 and 7 and chapter 4. So that's it. Any questions? And there's a lot to digest there, but we'll have plenty of opportunity to come back and use these in interesting contexts.